Okay, this equipment is called digital load meter. This is a load cell. It collects the data all the way through the load cell. The wire is connected all the way here to there, to the load cell. Now, this is the data acquisition. We call it VDash system B. Now, I've connected this output to the input, yeah, and this one is connected to my laptop. Now, this is extensometer, so I've connected the extensometer to here, and then I've connected this extensometer as well, which is micrometer, which can measure up to 1 micrometer, 1/1,000,000 of a meter, so it can measure 1,000 of a millimeter. I connected that one, and we put the specimen here. That is where we put the specimen. Now the specimen we are going to test is the Turing specimen, and that is 0.4% carbon as drawn. So this is what we're going to put. I will put the specimen here. I will show you how to load the specimen. Okay, first thing what you need to do is, for the specimen to put that one, you need to make sure you put that one in there. To put the specimen, let me just disconnect this one and I will connect it later. This is in the extensometer. You just lose these two screws and you put the specimen. Before you put the specimen, you measure the dimensions. I've already measured the dimension of the specimen, so I will pass it on to you. Now let me just close that one. So if someone can hold that one, because it's quite difficult to hold both sides. Yeah, from there. Yeah, yeah.
That.
Yes. Yeah, that's it. So I tie this one. That's it. Thank you. So now the specimen is in place. You can see the specimen is there. Hold. Now this is micrometer. Then you set the micrometer to 0. Now if there is an extension, it will just measure the extension of the specimen. Now when the specimen extends, this thing is going to move and it will record the reading. Yeah, so this will, let me just set it again. Yeah, so you can see if I just very sensitive, even if I put a little bit force, it goes there. Yeah, so this one is quite sensitive. It will just record that one. Yep. Okay. Now we will put the specimen in there. We will load the specimen. To load the specimen, this is what we do. We just put this one, 2 sleeves there. So collars, not sleeve. And then we just put the sleeve on the top, and this goes straight there. But before we do, we just need to move this thing back. So we just put that one there, and then we just put the pin to just secure that thing. Oops, no, not properly done. Not aligned properly. So let's do it that way. And let's put this one here. So that part is done. Now I have to do the other bit. So if you can just move it back, all the way back. So I can get rid of these things. Okay, now I'm gonna put the same thing here. Oops, sorry. Put the same thing here. And this, I put the sleeve there. And then I just bring that closer. Lift back. That's it. So, and I just put that pin there. Now you can see there is a little bit slack. We need to remove the slack, and we also need to actually attach this wire for the data acquisition. So I just put that wire here. Now this is connected straight, and this is connected to, because it's communicating here, and it's connecting straight to my laptop. Now we need to reset this thing to 0 position. So that's reset to 0 position. Now what we can do now is I need to actually remove the slack. So if let me turn it on and off. Let's load that one again. Okay, the force right now is 0. So if there's a little bit slack, so let's remove, oh, not like that. There is one other pin we have to hold here, so it actually and there's a hole we have to line. Yeah, and we need to make sure the load is 0, so there is no slack. So now this is difficult to move, so we're just going to move that one. So you can see it's just this thing is moving. You can record the extension, but the force here is still 0 because there's a slack. So we just keep doing it until this force try to increase, and then we can decrease the force. Oops, sorry, my fault. Yeah, there's still a slack. So I've just moved it to around 2 millimeter, and still, oops, sorry. Here you go, you can see the force increasing, so that is 0. Yeah. So yeah, the force is 0. I'm just going to reset this thing, set to 0, and I need to set this thing to 0. Okay, let's zero that one. Okay, now after that one there is a software. You can download that one. I just put the link. This is the software. Let me just close that one. Okay, and let me just put that one. I just downloaded the software. I just put the link for you. It's called the VDash Versatile Data Acquisition System. Now we have to add all the details. Now this has one ring, so you can select that one, normalize one ring component. Now the specimen, the total length of the specimen is 110. Yeah, final length we don't know. We need to see after the specimen is broken. Is specimen initial length is 60. Now this is test length is 60. Now this is the length that we are the gauge length. The gauge length of the component is this length. This length is known as gauge length. The total length is 110. That's in the manual, so you can find the value in the manual, and this is called the gauge length. The diameter was 5.05, so I put that one as 60. I changed the value to 60. Initial diameter is that. Final diameter I don't know, so I'm just going to get rid of that one. Initial cross sectional is, yeah, it just calculated from here 20.03. Final cross section diameter we don't know, so we will do that one later. Initial specimen length is 110. This is the total length. That length is 110. Yeah, so from all the way from here to here. Okay, now I don't have the load and that one. So if I start the specimen testing, I got 2 different gauges installed, and this one is not relevant. Okay, now I'm just going to start moving that thing. start turning that bit. 1 second. If I start the, oops, sorry, record that bit, 1 second. I need to measure the data after every 0.5 second. So I'm just going to start the data acquisition now. Yeah. If you start doing that one, yeah, keep going, keep going. And I can see here the load is increasing now. Yeah, the peak load, if I click on the peak load, which is the maximum load, is there as well. So as he's moving this thing, the specimen is elongated. It has elongated to 1.3. 1.3. Do not worry about the negative. Yeah, that negative doesn't count. It should be positive. And you can actually see here, there's a gap has been created already. You can see here because this is being elongated. Yeah. So just keep tying this one, so because there might be a change in cross-sectional area, and hence we will put the value. So it has just broken now. So now I need to take the specimen out, and then I need to record. Sorry, let's put that one there. I need to record the readings. Now what we need to do is we need to measure the diameter, the final diameter. So if I want to measure the final diameter, just turn it on. The 0.8. Now when we measure the diameter, we measure it as close to the failed specimen, and we just take like multiple readings. So make sure I got 3.03 millimeter. Now I'm just going to do that one here as well, like if that's a less, is 3.61. So 3.61, let's do that one again. 3.25 and 3.61. So I can take an average. And I can put here the final specimen diameter 4. So 3.4. Now I need to measure the final length of the specimen. Let's zero that one. So for that one, we have to put the specimen very close together, and we just so it's 113.87. So I write it down, 113 final cross-sectional. It's already calculated the final cross-sectional area. Initial length is here. The final length is 113.87. Yeah. Okay. The maximum load is 17.4. Yeah. Now strain, now here the value, you got the strain negative value, ignore the negative value. Yeah, percentage elongation is around 6.5, percentage change in area is minus 54.7. Minus mean it has reduced, positive mean it has increased. Now not sure why on the here extension is minus 4.81. yeah, it should be a positive value, positive 4.81. yeah, so make sure you do that one positive. Now I'm just going to stop the test, and this is data series 1. This is 1030. If I put that one, documents 1030, if I load that thing, so now you can actually see this data. Now you can see the data. That was a test specimen. Yeah, what was a specimen? 0.1% normalized. 1. Initial length was 60. Initial diameter is 5. Final diameter here, it says 0000. Yeah. Yeah, and here you got 3.4. You can see the final diameter is 3.4. Yeah.
Yep.
Okay. Now you can see initial cross-section area is 20. The final cross-section you say 0, 0, and then it says 9.8. The reason is because in the start I was not applying a load. When I'm not applying a load, it wasn't doing anything. Now, initial specimen length is that one. Final specimen length. Okay, 37.25. No, it's not 37.25. It's 113.87. Yeah. I'm not sure why I put that one. 130. Let me change this value. 100 and what was the value? 113.87. So 113.87. I'm just going to change that value all the way down, all the way down. Oh, here you go. Okay, that's it. So I just changed the value, all the values, 113.87. Load initially was 0.02, and as you can see, the load is increasing all the way until it reached the maximum load. Now this load is in kilonewton. Peak load was 17.4. That's the maximum load. Yeah, they already calculated the stress here. It already calculated the stress here, but make sure when you calculate the stress, you just find the stress is right. Yeah. So make sure you find the stress, the values are right. So double check all the stress values. Yeah, stress is force divided by the area. So force divided by the area. Force is in kilonewton, convert that into kilonewton, and the area you can keep in millimeter. Yeah, when you do that one, the answer will be automatically meganewton per meter. Yeah. Okay, the strain value here, that is a negative value. Make sure you consider that one as a positive value. Yeah. Okay, this is a percentage elongation. Percent elongation you have to calculate. The percentage elongation has a formula. The formula for the percent elongation is on the board. Yeah. So percent elongation is change in length over original length multiplied by the 100. To find the change in length, it's the original length plus the final length, and then percentage reduction in area is the formula that's down there. It's the final area minus the original area divided by the original cross-section area. The material will be more ductile if it has the higher value of percent elongation and high reduction in cross-section area. Yeah, so you can have the values from here. Now if you come back here, please. Now you see that one here. So here just ignore these values, percentage reduction, and you need to find that one, just one value all the way, because we cannot measure values at each and every point. Now you got this one, digital scale overall extension. Yeah, digital scale overall extension. This is the old, it says negative value. Ignore the negative value, consider this one as a positive value. Yeah, so from the start all the way, consider the value, change the value to positive. And all these values should be positive because it was not compressing, it was stretching. So these values, you need to analyze these results. Yeah, so I will put these results SM1002 data 1130. Now this 1130, the material we used was 1 ring 0.1% carbon normalized. So I will put that one there. I will just rename it and I will upload that one. So this is what you need to analyze. You need to create a stress strain graph. You need to also create the stress strain and the force extension graph. So two graphs you need to do that one, and then you need to analyze the results. Yeah.